Polynomial functions are functions that are fairly easy to graph, and the things that we like to graph after we've done a lot of graphs with lines and parabolas. The thing that makes polynomial functions a little bit of an easier thing to graph is that they are defined over all real numbers, and there are no holes or asymptotes or breaks in the graphs when we have a polynomial function. Now, to graph polynomial functions, we'll want to get some key parts to it and then draw in the rest of the curve. So we'll want to find any y-intercepts, any x-intercepts that it has, and also look at end behavior, possibly symmetry, and then go ahead and find some values of x plugged through that we'll get y coordinates out of, then to draw our graph. Now, first of all, let's think of what is a polynomial function. Well, a polynomial, recall, is an algebraic expression in which all the exponents on the variables are whole numbers. So the exponent on my x in the first term is an exponent of 4, 4 is a whole number, and an exponent of 2 on my second term on the x, and 2 is a whole number. And I don't have any fraction bars with letters in the denominator of the fraction. I don't have any negative exponents, and so I have a polynomial function here. Now, with polynomial functions, when you look at the highest degree term, if the highest degree term is even, the end behavior will either be like this or like this. Then once I look at, and here my highest degree is 4 and 4 is even. Now I want to look at the coefficient in front of my highest degree term to see which of these two cases our specific example is. And if the coefficient in front of the highest degree term is negative, and we'd already taken account that with the highest degree that's even, it's one of these two cases, and then with a negative lead coefficient, they call it, it will be the one that is pointing down. So I know my end behavior at least looks like this part. Now the next thing is I want to try to figure out what's going on in the midst of the central part of the graph. So we'll want to find our y-intercept and our x-intercepts. Now remember, to find a y-intercept of anything, you take out the x's and plug 0 in for x and solve. So with this particular function, our function value at 0 is the opposite of 0 to the 4th plus 4 times 0 squared. So that gives me 0 to the 4th is 0, and then the opposite of 0 is 0. 0 squared is 0, 4 times 0 is 0, and then 0 plus 0 is 0. So I have a y-intercept of 0, 0. Next, for our x-intercepts, we set y, or the function value, equal to 0. So here I have 0 is equal to the opposite of x to the 4th plus 4x squared. Well, that gives me 0 is equal to, and to solve this for x, I want to solve it by factoring. I have a greatest common factor of x squared, and because my lead coefficient is negative, I'm going to pull out a negative x squared. So when I divide out a negative x squared, that will leave me a plus x squared and minus 4. And then we have the opposite of x squared times x squared minus 4 factors as x plus 2, x minus 2. So I have two factors of x on the outside of the parentheses, and that will be 0 if x is 0. And then x plus 2 will be 0 if x is equal to negative 2. And x minus 2 will be 0 if x is equal to positive 2. So I have my x-intercepts of 0 for my x gives me a 0 out for y. And then there's two factors of that. So I actually have two x-intercepts of 0, 0. And then I have, if x is negative 2, I'll get a 0 out for y. So I have negative 2, 0. And if x is equal to 2, I'll get a 0 out for y. So I also have 2, 0. Now the reason I wanted to write both of these x-intercepts of 0, 0 that we got here, because we had that power of 2 on this outside factor of x, is that if you have in your x-intercepts an even number of times that the same x-intercept occurs, then your graph will touch it, that x-intercept, but stay on the same side of the x-axis as it came from. If it happens an odd number of times, like if it just you have one of those x-intercepts, then it actually goes through the x-axis to the other side. Now, I know that we have our end behavior looking like this. So I know it comes from below, does something, and goes back down. I know it has to go through the y-intercept of 0, 0. And then within the x-intercept count, I have 2 times that the x-intercept of 0, 0 occurred, so it's going to bounce off that dot. And then it also has to go through negative 2, 0, and it has to go through 2, 0. So let's graph those values. I have my 0, 0 for my y-intercept. I have 2 x-intercepts of 0, 0. Then I have negative 2, 0 as an x-intercept and 2, 0 as an x-intercept. Now what you could do next is make an xy chart where you plug in an x value that's left of the leftmost x-intercept. So plug negative 3 through your function to find out a y value there. Between each pair of x-intercepts, so you could plug in negative 1, you could plug in 1, and then plug in a value for x that's larger than the largest x-intercept. So you could plug in, say, 3, and get some y coordinates out to get an indication of drawing your graph. Because we know these pieces, we could actually just kind of rough sketch it from what we already have. I know it has to come from below. It has to go through the ordered pair negative 2, 0. It's got to touch this 0, 0, but stay on that side of the x-axis because I have 2 of them. And then it has to go through this point 2, 0, and then cross over to the other side, and then continue down. So this is the graph of y equals opposite of x to the 4th plus 4x squared, or if we use our function notation, f of x equals the opposite of x to the 4th plus 4x squared. And there you have an example of graphing a polynomial function.